Hi, this is Dr. Nerz. I'm in my dining room. Hopefully this is the second to last video boost of the semester. You'll be very relieved. I only have 40 minutes tomorrow and I'm kind of nervous about it, but I'm going to be talking about solvents in SN2, E2, E1, and SN1, and I'm mainly just going to give you notes. So I really want you to watch this video. It's important. Okay, I'm not going to keep shoving new stuff at you, but I really want to finish this little unit, and there's like probably an hour's worth of work left to do. We've been going very slowly. I know it doesn't seem that way, but we have been. So what we were starting to talk about in class was how solvents are involved in reactions. And one of the things we said was that when you go down the periodic table, nucleophilicity does not parallel basicity, okay? And so what we said is as the atoms get larger, like as you go from F minus to Cl minus to Br minus to I minus, the nucleophilicity increases this way, but the basicity increases this way. And this is kind of an important point because we were really basing, no pun intended, all of our predictions on basicity, on Bronsted basicity and pKa's, which are based on hydrogens coming off and the stability of the bases that are formed. So this idea of nucleophilicity is a little more complex. It's the idea of hitting a carbon, and it's not as simple as hitting a hydrogen, and it's not exactly the same. So what we find is we go down the periodic table, that nucleophilicity, the ability to hit a carbon, increases. And as I was saying in class, this is really a solvent-dependent phenomenon. So what I was saying in class was that as we go down the periodic table and you go from fluoride to chloride to bromide to iodide, you're basically you are decreasing the charge to surface area. Now this is not something that's really measured, it's just a way I describe it, but you're kind of decreasing the charge to surface area ratio. So here basically we have a negative charge on a little tiny ball, bigger ball, bigger ball, bigger ball, okay? So you would expect then iodide to be a really weak base because the charge is spread over this entire surface. It kind of goes along with our idea of dilution of charge. However, and then you would expect fluoride to be the strongest base of the series. It's not the strongest base, it's just the strongest base in the series. Remember, everything is relative. So what I said in class was because this is the strongest base, it tends to interact with solvents the most. And in particular, this phenomenon is most evident in protic solvents. So as I said, it's a solvent-dependent phenomenon. In fact, if you take fluoride in the gas phase, it's actually a pretty good nucleophile. So the solvents get in the way. So what's the deal with the solvents? Well, because fluoride is such a strong base, okay, if it's in the presence of a protic, I'm going to give it a little more space. If it's in the presence of a protic solvent, and a protic solvent, how am I doing on time?
3, almost 4 minutes.
Okay, a protic solvent is a solvent that can H-bond. And I know a lot of people are not up on their H-bonds. We're going to go over this in class. But basically, we're talking about water and we're talking about alcohols as solvents. These species have the ability to be hydrogen bond donors and acceptors. So it's dependent on hydrogen bonding. So when you're in protic solvents, what happens is fluoride, which is such a strong base, interacts really strongly with the protic solvent. And of course, it's going to interact with the delta plus part of the solvent. Etc. So this would be like a ball of solvent. And as I said in class, the fluoride in 3 dimensions is traveling with a ball of solvent around it. Now, what you'd expect for iodide, because it's a weaker base, it wouldn't interact with the solvent as much, and it would be a little freer to react. This phenomenon is probably also related to the polarizability of the atoms. The big atoms have a tendency to be their electrons tend to be very loosely held, as we discovered in bromination reactions. So this is very tightly solvated, and so it's not like a free anion. It's not free to react. So what we find is that we can really increase the rate of the bimolecular reactions. Those are the ones that are SN2 and E2 if we do the reactions in what are called polar aprotic solvents. And finally, we're starting to learn the importance of a solvent in a reaction. Solvents have so many roles, right? They create a medium for the reaction to take place. When you're refluxing, they create the temperature of the reaction. They have like so many roles, but they also can either impede or accelerate a reaction depending on what the solvent is like. So our problem is we've got to get our base/nucleophiles into solution, but at the same time, we don't want them so tied up with the solvent that they can't react. And that is the problem. That's one of the reasons bromide is a halfway decent nucleophile, because when it's in a protic solvent, it's kind of free. What we want in general are free anions, okay? So we can increase the rate of these reactions if we do the reactions in polar aprotic solvents in general. In other words, avoid the hydrogen bonding solvents that I just described. So what are some examples of polar aprotic solvents? One example is this, which is acetone. I've been using this in class a lot. Another polar aprotic solvent is this one, which is called DMSO. DMSO stands for dimethyl sulfoxide. This solvent is called DMF, dimethylformamide. Drawn like that, DMF. You'll see these in your textbook. Again, this one is DMSO. Now, if you see the acronym or you see that structure, you know it's the solvent. I'm going to put them below the arrow. What's special about these solvents? These solvents, the delta minus is on the exterior of the molecule, but the delta plus is on the interior of the molecule. Delta minus, delta plus. Delta minus, delta plus. Okay? Interior of the molecule. Somebody mentioned to me THF, which has come up every once in a while. THF is also a polar aprotic solvent. The delta minus is here, the delta plus is on the carbon. Okay, now, what's special about these? I want you to think about it. They solvate anions well. Oops, they don't solvate anions well. Backwards. They solvate cations well and anions poorly. So think about this. If we're going to get, say, supposing we want to get sodium methoxide into solution. If we want to get it into solution, we've got to get the sodium ion in solution, and we have to get the methoxide anion into solution. This would really be a solid, and you'd have to get it into solution. This sodium, okay, would be solvated extremely well by these solvents because the delta minus is very accessible. But these anions would not be solvated very well by these solvents. And because of that, the anions are more like free anions, and they would react much more rapidly.
9 minutes.
Okay, so on the next video, I'll continue with this a little bit in regard to E1 and SN1. But I want you to think about the fact that to get an SN2 and E2 to react fast, we need the strong base to be available, and to be available, it shouldn't be solvated well, and it's going to work better in this kind of solvent. Thanks.